Yeah. Okay, folks, can you hear me okay? Can you hear me? Okay, great. So let's get this show on the road. You guys can see that okay, I hope. Let's see. So today we're going to continue our discussion of partial wave analysis of scattering. And so the main goal today is to understand and use scattering phase shifts. All right, that's the plan. And so let's see. So to sort of get back up to speed on this slightly weird topic, you know, I know that the first time you see scattering phase shifts, it's not a very intuitive concept, but it's actually, you know, fairly straightforward. And I want you to kind of understand the philosophy of it. And so let's just kind of remind ourselves a little bit about scattering. And so we know that the most useful basis for scattering, meaning the most useful solution to H psi equals E psi, is this, right? I mean, it's this little guy that we know and love. We have an infinite wave, and then we have our scattered wave. F of theta. This is our scattered wave, an outgoing spherical wave. And that's something that we see that's for large R, you know, far from the scattering potential. And then we love this because then the differential cross-section, the most important physical quantity that we measure experimentally, is simply the scattering amplitude squared. So there's this beautiful relationship between differential cross-section and the wave function. But it turns out that there's another useful basis, is the basis that has rotational symmetry. And this is another useful basis for when we have a potential that is spherically symmetric. It only depends on the radius r, in which case then another useful basis is the basis where the quantum numbers are k, l, and m in spherical coordinates. And then we have the wave function is the radial part of the wave function times the spherical part, YLM. And this is another basis. And this is a basis that has well-defined angular momentum. Because you see the scattering basis does not have well-defined angular momentum, the first one that I wrote. But so then in this basis, then for this new other basis, and I'll put a dashed line between them, these are two different bases. And for this bottom basis, then we see that at large r, far from the potential, then we see that we can write the radial function, the radial wave function is approximately equal to some constant times a spherical Bessel function plus a phase shift. And that's because far from the potential, the particle doesn't feel the potential, the particle is free. So the free particle wave function is a spherical Bessel function, but because the wave function got sucked in a little bit at small r, the phase is slightly shifted. And so that is reflected even far away from the potential. We still have that phase shift. And so we remember that for a free particle, For a perfectly free particle where there's no potential, then we see that the phase shifts are 0. But if I have a potential, then I just want you to see the picture. This is the thing. So if I have a, then let's see if I here's my Bessel function. And so if I have if my potential is here, v less than 0, for some attractive potential, then you see that if this is for the free particle, then in the presence of the potential, you see it gets sucked in a little bit. And so then I get a phase shifted potential, or a phase shifted wave function. And that's the origin of the phase shift. Okay, so I want you to understand that. And this is all at fixed energy. So this is all happening at some fixed energy, and K is the variable that tells me the energy, just reminding you. And so then we see that then what happens is then what we can do is there's a mathematical trick, which I did last time, and the mathematical trick comes from when we take this wave function psi k of r is equal to e to the I k dot r plus f of theta e to the I k r over r, and we write it in terms of a sum over rotationally symmetric components. Well, I won't say. I'll just say we make it a sum over all these components. And so when we do this sum, when we do this math, and we write our wave function as a sum over angular momenta, which we do, it's just a math trick. And I showed you the math trick last time. I'm not going to go through all that again. Then you see that there's this beautiful thing that we notice. We notice that the scattering amplitude can be written in terms of, in this funny way. We see that the scattering amplitude can be written in terms of the phase shifts. And this is not obvious at all. But I mean, the math, it's easy to derive. We derived it last time. It's not the kind of thing you would have come up on your own. But once someone shows it to you, I think it's pretty straightforward. And we derive this this formula: e to the I delta L sine delta L. And I just want you to know that this is at fixed energy, and so delta L is a function of energy. I just want you to keep remembering that we're talking about the scattering at one particular energy. The energy is well defined. So this is the most important result for a partial wave. That's it. I mean, this is the big result. That's like the big climax. So that's it. The climax came and went. All right, that's it. That's the climax. Is this formula. So, but then of course the you know, from a practical point of view, what is we still have to find the deltas, and we have to figure out how to find those phase shifts. That's the next thing. But before we go on to do that, there's a very, very nice thing to notice. There's one more nice result. One more very nice result. There's actually two more, but I'm only going to emphasize one. One more very nice result is calculate. If we calculate the total cross section, then something very cute happens. There's a very beautiful result that is like a very famous result, and so we're going to derive that. So the total wave function is, the total cross-section of the scattering cross-section is the integral of the differential cross-section, of course, over all solid angle, right? Solid angle. And so, so let's calculate that using this new formula that we derived from the partial wave analysis. And so the new formula tells us that sigma total is equal to, because this thing we know is the scattering amplitude squared. So we see then that we can write, we have the scattering amplitude squared, d omega, and so we can do a, so we can do so we can do this integral. Let's do it. Solid angle. And so let's plug it in. And so we have the scattering amplitude is up there. So let's do this integral. It's an integral over solid angle of d omega. And so I got to plug this formula into here. And so now we're going to do it. So it's big and ugly, but it reduces to something nice. I have 1 over k squared. 1 over k, well, let's just write it as 1. I got 1 over k times, I got a sum. Let's see, do it like that. Actually, wait, let me try to make this neater. 1 over k times the sum of L equals 0 to infinity, 2L plus 1 square root, to do this, before I do this, let me just remind you of something. I'm going to use this little trick that you guys have seen before in some class, but I'm just going to remind you that PL of cosine theta can be written in terms of, does anybody know? Just curious, it's a little math trick. Does anybody know there's a cute way I can write the Legendre polynomial that we're going to use right now to help make this integral easier? Can anyone guess what the trick is? Tricks? Anybody? Any math tricks? Can you guys hear me? You guys can hear me, right?
Yeah.
Okay, just no one's up for math tricks this morning. Okay, let me tell you the math trick. The math trick is that the Legendre polynomial is exactly equivalent to, square root of 4 pi over 2L plus 1 times, here it comes, YL0 of theta phi. Haha! It's the same as the L0 component of the spherical harmonic. So that's a math identity. You've all seen that before in some class. And so what we're going to do is replace this component in the formula with the spherical harmonic. And so when we do that, then now back to this formula down here, we have 2L plus 1. And now we have the square root of 4 pi over 2L plus 1 times YL0 theta phi e to the I delta L sine delta L. And then we got to multiply it times the next guy. And I don't have enough space there, so I'll write it underneath. And it's going to be 1 over k. But now I got to do L prime equals 0 to infinity because I'm multiplying them and I have to give it another index so I can keep track of everything. And it's going to be, so now it'll be 2L prime plus 1 times the square root of 4 pi over 2L prime plus 1 times YL prime 0 theta phi times It's an asterisk because it's complex conjugate. E to the minus I delta L prime sine delta L prime. And there you have it. All you got to do is that integral. And it looks so hard, but it's actually really easy because what we see is the integral goes the integral. If you might already see it, because in the integral I can move all the constants out, and I'm going to have everything is proportional to this. I'm going to have this integral of d omega of YL0 of theta phi times YL prime 0 of theta phi star d omega, and this is equal to what? This is such an exciting moment. I know you're just as excited as me. What is it equal to?
Delta L prime.
Exactly, because spherical harmonics are orthogonal. Exactly, delta L prime. And so that means that L prime goes to L, it collapses. It collapses the sum. And so that's really great. So that means in this whole thing, every L prime I can turn into an L. And that's a very beautiful thing because you can see now how the e to the I delta L times e to the minus I delta L prime, which you see in this integral, now goes to what? Someone tell me.
1.
Exactly. And so everything becomes really simple. And so I'm just gonna skip some of the steps. It's just a little line of algebra, but then when you plug everything in, and it's really quite easy, you see that the total cross section, and remember this is for at one particular energy, is equal to 4 pi over k squared times the sum, L equals 0 to infinity, 2L plus 1 sine squared delta L, where the delta L is a function of energy. But look at that. Now this is why everyone really loves phase shifts. That's a very cute and very simple little formula. Look at it. I mean, it's so elegant. I mean, you know, that's pretty cool. So if you didn't believe in phase shifts before, you certainly believe in them now, because that's like everybody's most favorite little phase shift formula. And so you see that. So the bottom line is he who knows the phase shifts, then that person knows the scattering. Because if you can get the phase shifts, then you know the scattering cross section, and the scattering cross section is what you measure in an experiment. So you can see that the phase shifts are actually very physical, very real, very important, and give you all the most important information is in the phase shift. Okay, so the question then is, how do we find the phase shift? And the answer is easy. There's a very simple way to do it. Because look, let's remind ourselves what the phase shift is. So here is this is the picture. Okay, going back to this picture, I'll put a little star here. 2 little stars, that's where I'm at. You can see that you can see that the phase shift is simply the difference between the free particle solution and the solution when you have the potential. So this is this is in the asymptotic limit. Asymptotic means large R. Large R. So what that means then is to find the phase shift, then what you got to do, here's the strategy. It's a very straightforward strategy. what we do is we solve. So if we're given, this is a thing, you're given a potential. Someone says, I'm scattering a particle off this potential. What's the cross section? Someone says, you know, what's the total cross section? And then you say, oh, it must be this formula for the phase shifts. That's what you say. And then you go, okay, now I have to find the phase shifts. Then must find phase shifts. And so to find the phase shifts, what you do is you solve Schrodinger's equation, h psi equals e psi, in spherical coordinates to find the radial component of the wave function. You find the radial component that solves the boundary condition. So you solve Schrodinger's equation, and it has to solve the boundary conditions. So you solve it, and then basically compare the solution that you solve to the free particle solution. And what is the free particle solution? Someone tell me, what is the free particle solution of the radial component of the wave function for a free particle? Somebody tell me.
The spherical Bessel function.
Yes. That's exactly right. So you compare REL of R to the free particle solution. And where do you compare them? Where in space? Do you compare them close to the potential or far away? Somebody tell me.
Far away.
Yes. You compare them at large R. And when you compare them, what will you notice? Will they look the same or different? Somebody tell me.
Different.
Yes, exactly. Perfect. In what way will they look different?
There will be a phase shift between them.
That's exactly right. And so you will then measure that phase shift, and that phase shift is the phase shift. That's it, okay? So you look at them and you compare them, and they will look different, and the only difference will be the phase shift, and that is the phase shift, and you're done. So you compare them, and then what you notice they differ by a phase shift. And that phase shift is the phase shift, the thing we're talking about. And then you are done. Okay, that's it. So it's actually a very straightforward strategy. That's why these phase shifts are actually quite useful. It's not that big a deal, and there's a very simple, straightforward protocol for finding them. But of course, to find the phase shift, so it's not like we can't just write down a formula for the phase shift. Every problem is different. You have to solve the Schrodinger equation, match the boundary conditions, find the radial wave function, look at it asymptotically, and see how it differs from the free particle solution. That is the phase shift. So I can't just write down a formula for it. I can tell you the protocol, the strategy, but every problem is different. So let's solve one. So let's do an example. Let's consider some potential. So let's consider some potential, and then let's find the cross section let's find the total scattering cross section using phase shifts. Using phase shifts. Okay, which potential should we use? So let's do an example. So let's pick a very simple example. Somebody tell me what example should we do?
Hard sphere.
Good choice. Very good choice. Excellent. Let's think of the simplest potential, and that's the hard sphere. Let's consider the hardball potential. What happened there? Hard sphere potential. And we all know what a hard sphere is. It's infinity for r less than or equal r naught, and it's 0 for r greater than r naught, right? That's what a hard sphere is. And so it should be the simplest one, but we saw that we remember that we cannot use the Born approximation for this. We cannot use the Born approximation, which tells us that d sigma d omega is proportional to the matrix element, right? And the reason we couldn't do the Born approximation is because when we try to calculate this matrix element, it equals what? For the hardball, it goes to what?
Infinity.
That's right. So the Born approximation fails for this example because the potential is too big. And the Born approximation is only for a small potential. But the partial waves don't care. Partial waves don't care if your potential is big or little. Partial waves are always work. The partial waves only care that your potential goes to 0 at infinity. All right, that's what the partial waves just. So for let's do partial waves. Partial waves only care that the limit of r goes to infinity of v of r goes to 0. Okay, the potential has to go to 0, and there's actually a certain rate that it has to go to 0 at, but we won't get into those nuances. Okay, so let's solve it. So let's do it. And so we have a potential. So we have v of r is equal to infinity for r less than or equal to r naught. It equals to 0 for r greater than r naught. Oops, r naught. And so now we must find so now we want to remember we want to find the cross section. So we need to find the scattering phase shifts, and to find the scattering phase shifts at a particular energy, we have to do what? So what are we going to do now? Somebody tell me, what are we going to do?
Solve the Schrodinger equation.
Exactly. That's exactly right. Stupid. I hate this thing. We have to solve H psi equals E psi, including the boundary conditions, right? Because you guys all know when you solve the Schrodinger equation to get all the eigenenergies, eigenstates, eigenenergies, blah, 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 you got to use the boundary conditions. So that's what we got to do now. And then what we're going to do is we need to find, and we're going to do it, we got to do it in spherical coordinates, must do it in spherical coordinates. And then we have to find REL of R, the radial component, right? Okay, so let's do it. And so, okay, so how do I proceed? Can anyone tell me, like, what do I do next? Does anybody remember how to solve the Schrodinger equation in spherical coordinates? What do I do?
Separation of variables.
Good. That's right. Separation of variables. And so the variable that we care about now is the radial component. So you're totally right. It's separation of variables. And so we're focused on the radial component. And so what do we do next?
You solve for the solution to the UR equation.
Exactly. That's good. Excellent. So we write down the radial Schrodinger equation and solve it, right? That's exactly right. Let's do it. So write down the radial Schrodinger equation and solve it. So let's do that. We won't exactly use the U. I mean, that's one way of doing it. We're not going to even bother that. Although, you know, that is useful also. But let's just write down the radial Schrodinger equation, and this is what it looks like. Negative h bar squared over 2m 1 over r squared ddr. Do I even have space? Oh, actually, I'm going to erase it from here and write it below. Here's the radial Schrodinger equation. Negative h bar squared over 2m ddr 1 over r squared ddr r squared ddr r e of r plus v of r plus h bar squared l times l plus 1 over 2m squared r l of r equals e r e l of r. Okay, so there's the radial Schrodinger equation. Okay, it looks familiar. You've all seen it. And so let's now, okay, so I wrote down the radial Schrodinger equation. Now what do we do? How do we solve this?
Boundary conditions.
Exactly. That's exactly right. It's the boundary conditions. So let's use the boundary conditions. And so we see that in the radial direction, we have v as a function of r. And the thing to notice is that this is one of those classic problems where there's a very well-defined boundary, and the boundary occurs at what point? When r equals what?
Or not?
Yes, exactly. So right here at r naught, we see that the potential goes to what? At r naught, the potential goes to what? It's a hard ball?
Infinity.
Infinity.
Yes. And over this whole region, it goes to infinity, right? And then over this region, it's 0. So so these are two regions. I'm going to call them region. So we got to set them up. And so this is region 1, and this is region 2. And so I'm going to have my wave function in region 1. Actually, I'll call it my radial wave function since that's what we're solving for. R, E, L in region 1 of R. And I'm going to have my R, E, L in region 2 of R. And then you know what I'm going to do? I'm going to say, eventually, I'm going to say that R, E, L in region 1 is equal to R, E, L in region 2. Where? Where? At what point are they equal?
At
Or
the
not.
boundary.
Yeah, that's right. They got to be, right? All right, that's how you do it. That's exactly right. And so then I'm going to find, and so what I'm going to do, my strategy then is to find REL in which region? Which region do I really care about the most? Someone tell me.
2.
That's right. And I'm going to find REL. I'm going to take R goes to what? To find the phase shift, I have to take R goes to what?
Infinity.
Yeah. I'm going to find REL in region 2. I'm going to take R goes to infinity, and then I'm going to compare it to what? To get the phase shift, I got to compare that expression to what?
The Bessel function.
Exactly. And I'm going to see how they differ. And they're going to differ by a phase shift, and that will be the answer, the phase shift, the magical phase shift. Okay, so let's do this. So let's consider these things. So in region 1, REL in region 1 is equal to what? Someone tell me.
0, because the potential is infinite.
Exactly. You can't go there. The wave function is 0. It's a no-go zone. That's right. It's 0. Excellent. Now let's do region 2. REL in region 2 is equal to what? Now, before we answer that, in region 2, the potential in region 2 is V of R equals what? In region 2.
0.
Right. So before you tell me what REL in region 2 is, let's just take a look. Because in region 2, this thing equals 0 in region 2. And so I want you to notice that in region number 2, my radial Schrodinger equation is, let's write it out, because I just want you to look at it closely. 1 over r squared, because there's something funny going on in spherical coordinates that it's not intuitive at first, but it can be intuitive if you stare at it for like 7 or 8 years. And then h bar squared L times L plus 1 over 2mr squared REL of R equals E REL of R. Okay, so that's the radial Schrodinger equation in region 2, right? You see that? Yeah, it looks good. I think I wrote that down correctly. Okay, now this is for V equals 0. I want you to see this is a free particle. Okay, but that's the free particle Schrodinger equation. But I want to ask you a question, so there's no potential, but I just want you to see that when I look at this thing reminds you of the kinetic energy operator, right? That's kind of like kinetic energy times psi. And when I look at this part, that reminds you of something else. It reminds you of what? What does it remind you of?
Of like a potential.
Yeah, exactly. It reminds you of the potential times psi. And so, and then this, of course, is, E times psi. So this is familiar to you. It's like a Schrodinger equation. I got a kinetic energy, got a potential, got the energy on the other side. And so, but then you see that this, but the potential is 0. So this is not really the potential. What is it? What is this thing? What do we call it? And
Like
you
the
thought of this,
centrifugal
yeah.
term?
Yeah, exactly. Good. It's the centrifugal term. That's exactly right. And so it's an effective potential. And you guys have thought about this back when you were doing hydrogen atom. You know, I know you guys all thought about this at some point or another. It's an effective potential. And so we have this effective potential, h bar squared L times L plus 1. And so the point is that even though the particle doesn't really, even though there's no potential, the particle feels a potential and it's a strong potential. I want you to see that, because it's basically saying that this, if I plot this effective potential, then you can see that it's equal to, Jesus Christ, let me do something, excuse up. You can see that it has these different values. You know, this is L equals 1, L equals 2, L equals 3. You know, it goes as, you know, it's a 1 over r squared. The effective goes as 1 over r squared. It's a really strong potential. It goes up, and it means that the particle really does not like to go to the origin. And so, you know, it pushes the particle away from the origin, pushes particle away from origin. And so this is a very important insight for you guys to see and to realize that there's this effective potential. Even though it's a free particle, if the particle has angular momentum, then it doesn't like to go to the origin. And that should not be mysterious. It is actually a very simple physical reason for that, because I like to think of this as the it's just rock. I call this the rock on a string physics, because you've all experienced this. You all have swung a rock on a string or something equivalent. Everyone has done that. I know that every single person, every one of you has done this. You got a string, you tied a rock to it or something like a rock, and you swung it in a circle, right? You've all done that. Actually, let me draw it better. You've all swung it around because you wanted to hit someone with it. And so you had to swing it and make it go fast so you could hit someone with it, right? You've all wanted to hit somebody with a rock on a string. You swing it. And then what you've noticed is that when you make the string R come shorter, then what does the rock do? You swing the rock, but now if you have put your other hand here and pull the string while it's spinning, like when you play tetherball, then what does the rock on a string do? Somebody tell me.
It rotates faster.
That's right. It rotates faster, and it starts pulling on you, right? It's like it goes faster and faster, and as it goes faster and faster, that means more of the kinetic energy is going, you know, into the speed. You know, the ball's going really fast, and so that is why it's hard for you to pull it, because you pull it and it goes faster and faster. And so you've all experienced that, and so that's what's happening here. This is the quantum mechanical version of that. So that means that there's this effective potential pushing the particle away from the origin, because the equations know that if I conserve, in order to conserve the angular momentum, because this is all at fixed angular momentum, if I want to conserve the angular momentum, and if I pull that rock in, it's going to go faster and faster. And if I pull the rock all the way to the origin, what will be the speed of the rock? If I was able to conserve angular momentum and pull the rock all the way to the origin, what would be the speed of the rock in your hands? Tell me.
Infinite.
Yeah, it'd go faster than the speed of light, and it would just start radiating neutrons and protons and all kinds of particles, you know, and it would explode, you know, and destroy the Earth. That's right. So that's why you have to be careful when you do that. So because, you know, you don't want to have the rock go faster than the speed of light. It will explode and kill everyone. That's right. So that's the whole point. So I want you to remember that. And so that physics is going on here. So now let's get back to our equation. And now I'm asking you, what is the radial wave function? Let's see. What is the radial wave? What is the solution to this equation in region 2? And let me ask you, and I'll just ask you another question. Does region 2 include the origin? Yes or no?
No.
That's right. So now I'm asking the question, what is the radial wave function in region 2? Well, part of the answer should be really simple, because the particle is a free particle in region 2. What is the wave function of a free particle?
A plane wave?
Well, in spherical coordinates. What is the solution?
Spherical
Yeah,
wave.
exactly. In other words, I'm asking you, what is the solution of this equation? This is the equation for the radial part, for the radial component of the particle for a free particle. This is the free particle Schrodinger equation. Remember, that's what we're talking about. And so, what is it again for a free particle? What is the solution to this?
A
It's the
spherical wave?
What's it called? Spherical what?
Bessel function.
Yes, the spherical Bessel function. Good. That's exactly right. It's a spherical Bessel function. J L of KR. That's exactly right. But it's not the full answer. It's missing something. Why is it missing something?
It needs the Newman functions as well.
Right. Why do we add the Neumann function? Why do we add it here? And we didn't do it before. What makes this day special?
We're gonna need it when we want to do our boundary matching.
We will certainly need it, but why did we reject it before? Why is when we talk about a free particle is a spherical Bessel function. It is not a spherical Neumann function when we talk about a free particle. Why are we now including the Neumann term?
The
When I
Neumann
write-
term, the Neumann term would go to infinity at 0, and that was not cool. But now we don't need to worry about it going to 0 at r equals 0, infinity at r equals 0, because the region 2 is at r naught, which is greater than 0.
That's exactly right. You nailed it. That's perfect. Exactly. Because what we always do when we're solving differential equations in different regions, we always have to write the solution of the differential equation in the most general terms and then match the boundary conditions. That's exactly right. You nailed it. The reason why we ignored it before is because to match the boundary conditions at the origin, we had to get rid of it. But now our region does not include the origin, so we have to keep it. That's exactly right. Perfect. So the wave function, then we have these two components. I'll call it, and I have to put some coefficient between them to make it general. And so that is our wave function. And so then we know that the next thing that we're going to have to do is we're going to have to find alpha L and beta L. Now, how do we find alpha L and beta L? We use what to find them?
Boundary conditions.
That's exactly right. So this should look very familiar to you. Okay, so now let's do it. And so let's do it. So here we have REL of R is equal to alpha L times JL of KR plus, I keep screwing up, beta L. Okay, So the next thing to do is to use the boundary conditions to find alpha and beta, but I'm not going to do that. I'm going to do something else instead. Instead, let's first consider the asymptotic solution. Because what I'm going to do is I want to find the phase shift. Because by considering the asymptotic solution, we can find the phase shift. And so I want to find delta L in terms of alpha and beta. And then I can find alpha and beta from the boundary conditions. That's what I want to do. Okay, so that's just the order of operations. So let's find the phase shift first. And then we'll find, okay, you get it, I just wrote it down. So to do that, let's go to, when we go to R to infinity, we see that the Bessel function is equal to, does anybody remember what the Bessel function looks like? When R goes to infinity, does anybody remember? Well, I'll remind you, on the bottom was KR, and what was on the top? Do you guys remember?
Sine of KR?
Exactly. And then there was this annoying little phase shift thingy, which is part of it. We'll just put it in there. And now we got to do the Neumann function. And the Neumann function, there's going to be, I'll give you a hint, there's a KR on the bottom, and what goes on top?
Cosine?
Yeah, exactly. And there's an annoying little negative sign too that we won't worry about, but there it is. We got to keep track of it. Okay, so and so what I'm going to do is I'm going to write this. So what we see then is I'm going to write it like this. It's equal to 1 over KR times alpha L times sine of KR minus L pi over 2 minus beta L times cosine KR minus L pi over 2. Okay? And before, okay, so, but before we go on, and this is for R goes to infinity, by the way. This is the large R expansion of the radial wave function. And so, but what I'm going to do now, before we do anything, we're going to use a simple trig identity. Let's use a trig identity. And this is a trig identity that you guys have all used before, but you might not have it memorized. And so let's be reminded. I'm going to remind you of a trig identity. This is the trig identity. If some function of x is equal to a sine x plus b sine x, then I can also write that f of x is equal to g sine x plus delta, where g is equal to, does anybody know? Does anybody remember this trig identity? You've all seen it somewhere or another. I know you have. Do you
Square
remember?
root a squared plus b squared?
Exactly. G equals the square root of a squared plus b squared, and delta is equal to what? What does delta equal? Actually, I'll do it. This is the more famous way of writing it. I say tangent of delta is equal to what?
B over A or A over B? B over A.
Yeah, you nailed it. That's exactly right. That's it. And so we would say then that delta is equal to inverse tangent B over A.
Is one of the Is that supposed to be cosine of x in front of the a? I mean,
Oh, yeah,
multiplying the a,
yeah. A sine x. Oh,
or
shit.
one of the.
Wait. A sine x is b cosine is a. Huh. Let me just get this. Okay, yeah. You're right. Thank you. Let me make sure that I do this right. Thanks. Okay, yeah. And then it's really easy to, let's prove it. Let's prove it. G sine x plus delta is equal to G times cosine delta sine x. I'm just expanding this. I'm just expanding sine of x plus delta using the famous trig identity that you guys all know, plus G sine delta cosine x. And then if I call this guy, then this guy is A and this guy is B. So A equals G cosine delta, B equals G sine delta. And so you can see that A squared plus B squared is equal to G squared cosine squared delta plus sine squared delta equals G squared, all right? And then the other one is, if I have this thing equals that and that equals that, then I can see, you see that B over A is equal to G sine delta over G cos delta is equal to tangent delta. Okay, so we just proved it. So we're, okay, so we're gonna use this thing. And so now let's use this little identity, because now we can look at our thing here and I'll call this, let's plug into the identity. So I'm gonna call this A, I'm gonna call this X, I'm gonna call this B, I'm gonna call this X. I'm gonna plug into this little identity and I'm gonna say that R E L R is equal to 1 over KR times basically, you know, G times sine of X plus delta, right? 1 over KR. Okay, but now I need somebody to tell me, what is G? Somebody tell me what G is. Tell me. Plug into that again. Yeah.
Alpha.
Say it again, please.
Plus, square root alpha squared plus beta squared.
Exactly. And then I have sine. What's X?
KR minus L pi over 2.
Yes.
And then the delta plus delta L.
But what's delta L?
Tan inverse of negative beta over alpha.
Exactly. Maybe I'll write it like, yeah, delta, oops, delta L equals tan inverse of, what did you say?
Negative beta over alpha.
That's exactly right. There you have it. And so this delta L that we just got from this little trig identity, what is the significance of this delta L, which we now have written right here? What is the significance of that, which we just calculated?
That's the phase shift that we were looking for.
Yeah, that's the thing, exactly. That's exactly right. Because what we have is that we have REL, just for those of you who might not have seen it, because it just kind of sneaks up on you. We have square root of alpha L squared plus beta L squared, but then we have this thing, which is sine KR minus L pi over 2 plus delta L over KR, but this is exactly equal to this square root of alpha squared L plus beta squared L times, but this thing is exactly the same as JL of KR plus what? Plus what?
The phase shift.
Is it like 2 delta L?
Exactly. So the delta L that we calculated here is the same delta L. So this delta L is telling us the exact difference in phase between our solution and the free particle solution. You see that? Because JL of KR is the free particle solution. And so we just calculated the thing, we got it. So delta L, the phase shift that we wanted all along, is right there. So let's write it here. It's tan inverse of negative beta L over alpha L. Okay, so that's the phase shift. So that's the magical phase shift. So we're basically done. You know, we're not done because we got to figure out what alpha L and beta L is. So, but we got the phase shift in terms of alpha L and beta L. So now let's find alpha L and beta L. So to find alpha L and beta L, remember we got this thing, you know, we got our region. This is R naught, this is V, and this is region 1, and this is region 2. And so I can write REL in region 1 at R naught is equal to REL in region 2 at R naught. And what is REL in region 1? What is that?
Zero.
Yes, perfect. And REL in region 2? Where is
L
it?
or something.
Let's go back to this guy. Remember this guy? Let's go back to this guy, okay? Because the thing is, the boundary is the boundary at R naught. Is that in the far field regime or the near field regime?
The near field.
Yeah, it's kind of close. We don't know exactly where it is, but it's definitely not the far field, right? And so I can't just use all that sine cosine asymptotic expansion. I got to go back to the correct solution right here, okay? So let's go back to this. So let's remember that the general form of the solution is that REL of R is alpha L of JL of KR plus beta L of times eta L of KR. Okay, that's the general solution. So let's use this general solution. And so here then, I have 0 equals what? What goes here? Somebody tell me.
That function that you went up for, but at the boundary.
Exactly. Alpha L times JL of K R naught. Do we know R naught? Do we know R naught? Is that a known thing? Yes or no?
Yeah.
We do know it. That's right. Times beta L times eta sub L of K R naught. So we get this cute little equation from the boundary conditions. And let's solve that little equation, because now I'll bring this guy to the other side, and I'm going to get alpha L Actually, let's write it like this. So I bring it to the other side, and I'm going to get negative beta L, eta sub L of K R naught is equal to alpha L, J sub L of K R naught. And then I can put one over the other, and I say I get negative beta sub L over alpha sub L is equal to J sub L of K R naught over eta sub L of K R naught. Oh my God. Look, we got it. We got it. Because then this thing I can plug into here. See? And so now we have it. We have the phase shift. We have it exactly. We've got the phase shift in all its glory. We have calculated it perfectly. There it is. You see it. It's a phase shift. We got it. So that's how you do it. Because the thing is that the spherical Bessel function is a function. Like, you know, you can look it up in a book or punch it into your calculator. The Neumann function is also a known. These are known functions. And so, and R naught is known, and K is known because K is just the energy, right? And yeah.
What symbol are you using for the Neumann function?
Eta. Eta. It's like a squiggly N like no. All right, that's called an eta. Eta. Professors always know those functions. We're good with the Greek letters. Okay, so there you have it. And so, but let's keep going. So now what we have then is we've calculated the scattering phase shift. And so now we know that the total cross section is really simple because the total cross section for the hardball scattering is going to be 4 pi over K squared times L equals 0 to infinity, 2L plus 1, it's just the formula that we derived, sine squared times delta L, where delta L is this, right? So we have the formula for delta L. It's equal to tan inverse of minus beta sub L over alpha sub L, which is that. Okay, so so that's it. And so that's the cross section for hardball scattering. We solved it. Exactly, no approximations even. That's the cross section for hardball scattering. But now let's consider some limits. Let's consider some limits. Let's consider the low energy limit. It's very interesting to look at the low energy limit. And the low energy limit means small e, but small e means small what? What's the important parameter that we're using here?
Small k.
Exactly. but just saying small k is not enough. And so it's really saying that k times R naught is what?
Small.
Much less than 1. That's right. So that's the low energy limit, okay? Because there has to be something that you're comparing it to. We're comparing it to R naught. That's sort of the important parameter in this problem. So this is the low energy limit, is this. It basically means that, you know, here's my ball, my scatterer, and here's my wavelength of my function of my particle. All right, so I have my wavelength of my particle is really long compared to the scatterer, where this is R naught. So that's the low energy limit, is this limit. And so let's consider this limit. And so the question is, what is the total cross section in the low energy limit? And so let's take that limit. And so what we got to do then is we see that what we have to do is we have to find basically, we know the formula for the cross section depends on these phase shifts. So we have to find the limit as E goes to 0 of the phase shift. Okay, so let's do that. And so what we see then is that let's take the limit, and the limit is really going to be K R naught goes to 0. And let's take the limit of the tangent of delta L, since that's easier, which is equal to the limit of K R naught goes to 0 of JL of K R naught over eta sub L of K R naught. All right, and so now we have to use these asymptotic limits of the Bessel function and the Neumann function. And so let's go, and so we go back to a book, we go back to some math book, and we look it all up, and we remember that the limit of R goes to 0 for the spherical Bessel function is equal to some funky thing, KR to the L over 1 times 3 times 5, blah, 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 times 2L plus 1, whereas the limit for R, and this is just stuff that you look up in a book, but it can be useful. And the asymptotic limit of the Neumann function is -1 times 3 times 5 times the absolute magnitude of 2L minus 1 all over K times R to the L plus 1. And so when I plug these two guys in to this, then what I see is that the ratio of those two limits, and I'll skip a few lines of algebra. It's pretty simple algebra. You guys could all do it. And I'm going to get K R naught to the 2L plus 1 divided by -1 times 3 times 5 times ... 2L plus 1 times 1 times 3 times 5, absolute magnitude of 2L minus 1. And so that's what we get. But then what we notice is that first, let's notice that this whole thing is small, right? Because you see how it's proportional to KR naught. So it's small, okay? Because we're taking the limit of KR naught goes to 0. And so tangent of delta L for small delta L is what?
Isn't it like 0?
Yeah, if it goes to 0, but right before it hits 0, what is it?
Oh, it's just delta L.
Exactly. So that's an identity that you guys all know. And so what we see then is that this thing is the phase shift, all right? So for low energy, then what we see is that the phase shift, delta L, is equal to this expression, which I don't feel like writing again. But now let's notice something else. Look, you have 2L plus 1 in the exponent. And so I got a small number to the 2L plus 1. And so you can see that as L gets bigger and bigger, that number, is it getting smaller or larger? Somebody tell me.
Smaller?
Yeah, because I got a small number to an exponent. And a small number to an exponent gets really small, crazy small. And so the biggest phase shift is when what?
L equals 0?
That's right. In the limit that kr goes to 0, that kr naught goes to 0, the L equals 0 component dominates. That's right. Because you can see that if you look at that expression, if L does not equal 0, then the limit for kr naught goes to 0 of delta L is equal to what? Look at that expression and tell me what's the limit for L not equal to 0. What's the limit? Someone tell me.
0.
Right. Because I have kr naught to the 2L plus 1. So if L is not 0, I have something to the exponent 2L, and that something goes to 0, so it goes to 0. But on the other hand, if L equals 0, then the limit as kr naught goes to 0 of delta L equals what? Can you see it?
-1.
That's right, but it's not exactly -1. It's going to be kr naught to the 1 divided by what? Well, in case those formulas look funny, it's -1. And so for L equals 0, delta 0 is equal to minus kr naught. So that's the L equals 0 phase shift. And so then the total cross section is equal to the sum. It's that expression for
On the sine square just goes to delta L squared.
Exactly. L equals 0 to infinity, 2L plus 1 sine, what was it? Sine squared delta L. And you see that they all go to 0. So all the phase shifts go to 0 except L equals 0. So then we see that sigma of t, the total cross section is 4 pi over k squared times sine squared delta naught. And for small phase shift, that's the same as 4 pi over k squared times delta naught squared, which is going to be 4 pi over k squared times kr naught squared. And so the total cross section is going to be 4 pi r naught squared. All right, so that's it. That's the total cross section. And this is, I just want to mention that this is 4 times the classical cross section. Because if I have a hard ball of radius r naught and I'm shooting BBs at it classically, then what is the cross section? Can someone tell me?
Just the area that it sees from the front.
Exactly, pi r naught squared. But now I see 4 pi r naught. And so it's kind of cute because now that's actually the surface area. It's just a funny thing to notice. It's the surface area. And it kind of makes sense because now in the long wavelength limit, I'm shooting these waves at it. And the waves are kind of wrapping themselves around it. You know, it's like it's diffraction. It's the long wavelength limit of diffraction. And the waves wrap. And there's an important thing to notice, just the last thing I'll say. Yeah, I just want to say one last thing about this, finish off. I'm going to go a few minutes over, but if whoever has to leave, just leave and you can look at the recording. Because I just want to say one last thing about this, since we're talking about it, because this is the end of this discussion, but this last point I want to make is that in general, for low energy scattering, then the phase shifts are dominated by L equals 0. The L equals 0 phase shift is the dominant phase shift. L equals 0 dominates. And when I say dominates, when you calculate the cross section, then the L equals 0 is the most important one. And there's a really simple reason for that, a really simple physical reason for that, which is that you have to remember that we have the effective potential. The effective barrier is h bar squared L times L plus 1. And it goes back to that rock on a string physics, because if you're spinning a rock on a string, then you have to realize that what's happening is that the effective potential felt by a rock on a string, it looks like this as a function of r, and as the angular momentum gets bigger, the potential gets bigger. So this is L equals 1, L equals 2, L equals 3, and for L equals 0, there's no potential. L equals 0 there's no centrifugal potential for L equals 0. And so what happens then is that if I have a low energy, and this is my energy, small energy, then you can see how the potential, if you're far away from the potential, your wave function is wiggly, but as soon as you hit the potential, what does your wave function do? Intuitively, from last semester. What does your wave function do as soon as you hit the potential? Like here's a potential, V, R, and if this is your energy, E, when out here on the right-hand side, your potential is wiggly because your energy is greater than the potential. But on this side, your energy is less than the potential. So what is your, what?
It gets small.
It decays. Right, it decays exponentially. Your wave function decays exponentially. And so the point is that if you have small energy and you have high angular momentum, then I'll ask you a question. Do you see the origin? Does your wave function make it to the origin if you have high angular momentum?
Not at all.
Right. Your wave function never makes it to the origin, but the potential is usually small at the origin. So what that means is that if you have a high angular momentum wave function, your wave function never even touches the potential. So if E is small and L is big, then your radial wave function never sees the origin. And the potential is at the origin. So your wave function never sees the potential. But if you don't see the potential, then your phase shift is what?
0.
It has to be 0. So that's the whole point. So if you have higher energy, if you have low energy, you've never come into the origin. And you can just see that because if you just plot the wave functions, like check it out, you can just see that in the Bessel functions, because if you just plot the Bessel functions, you see that this is the L equals 0 Bessel function looks like this. And you probably never noticed this before, but just plot the Bessel functions and look at them. That's the L equals 1. But now plot the L equals 2, and it does this. And now plot the L equals 3, and it does this. And that's why we had the J sub L of KR. Remember the J sub L goes to the sine of KR minus L pi over 2, because that's the part that's pushed out by the centrifugal barrier. So as you can just see it in the spherical Bessel functions, they get pushed out away from the origin as the angular momentum increases. You can just see it. And so that is a reflection of this physics. And so the point is simply that if my radial wave function never makes it to the origin, it never sees the potential, and so there's no phase shift. So that's why low energy scattering is always dominated by the L equals 0 scattering phase shift. And so if L equals 0 dominates, then we would say, we call that S wave scattering. So often out in the real world, you hear people talk about S wave scattering, and you're wondering, what the hell does that mean? Well, what it means is that the scattering process is a low energy scattering process dominated by the L equals 0 phase shift. That's what S wave scattering means. Okay, folks, that's it. That's where I'm going to stop. Any last questions or anything?
Is this
Okay. Yeah?
Is this the end of scattering then?
I'm sorry, what?
Is this the end of our scattering discussion?
Yeah, for the most part. I mean, that's all the scattering physics that I want to present in this class. I think what I might do next lecture, if there's time, I might show another example of this, but that's kind of where I'm going to stop. Okay, bye-bye.
Sorry, are you going to talk about resonances at all, or not really?
Nah.
Okay.
But,
Okay.
come tomorrow or come on Friday and we can talk about it all you want. Ask me about it on Friday. Okay, bye-bye.
I will do. All right,
Okay,
thank you. Bye.
bye.